All right, well, hello everybody. Happy Tuesday. So we're back here, both doing the Zoom broadcast and the live lecture. So whichever way you're feeling is best for you at this point, we can continue on. So the last couple chapters, or last couple lectures, we've been talking through chapter 8 and then subsequently chapter 9. We have a little bit to talk about here in chapter 9 yet today. So what I'm going to do is I'm going to go back to these little typed quick note slides that I put up on the Blackboard website. So you've probably seen that from the previous lectures. I'm going to talk about this last page first. And then from here, we're going to move on to chapter 10, which I like a lot better, as it turns out. Chapter 10, I think, is a pretty interesting chapter. There's lots of cool stuff that we're going to learn there. And I think that for your next exam, we're going to focus mainly on chapter 7 through 10. So that's going to kind of get us to the point where we can take that next exam. Just a little over a week now is our next exam. So it's on our radar already, okay? So that is the plan for today, all right? So let's just begin here in chapter 9. Now, one of the remaining topics in chapter 9, and this one is a little bit interesting, okay? Some of chapter 9 is a little bit of review of things we've done, maybe, or just not all that much fun. But this one's kind of interesting because what this allows us to do is ultimately compute or estimate, I'll say, the enthalpy of a chemical reaction, more or less any chemical reaction we want to, from a consideration of the bonds, the chemical bonds, which are involved in the reaction, okay? So basically, what do I mean by that, okay? Well, in the previous lecture, we talked about this slide very briefly. We defined some terms, one of which was our bond energy. You may remember that. We also talked about the bond length. And we said that this table was a listing of bond energies and lengths, okay? And there's multiple different columns to the table. Really 4 different columns it looks out like, and lots of different bonds, corresponding energies in kilojoules per mole, and then also corresponding bond lengths. And we said that in general, the higher the bond energy, the smaller the bond length. These are kind of just general trends, okay? But we're going to return to this table now and use it to our advantage to more or less estimate the enthalpy of reaction for any reaction we want to, just from solely a consideration of which bonds are present before the reaction and which bonds are present after the reaction, okay? So how do we do that? Well, if we look back at the equation real quickly, it's kind of one of these laws of summations, okay? I'll try to zoom in as much as I'm able to here, okay? It's one of these laws of summation. And what this equation basically says is that the standard enthalpy change for any reaction is equal to, and I say equal to, and I kind of hesitate to say that because this is really an estimate. I'll get back to that later, okay? But the enthalpy of reactions can be estimated by adding this term. One's going to be exothermic, one will be endothermic. We'll talk more about that here in a second. And basically, we're just going to combine these. So one's going to have a positive, one's going to have a negative. All right, now what does this equation say? Now, obviously, there's mathematical symbols here, but we can actually kind of just define it in words if we want to. This first term right here, we're summing up bond energies for the reactant bonds. And the key word here is broken. Our model for using this equation is that we are going to take all of our reactants, whatever reactants we're given, however many copies we're given, we're going to do an analysis of all of the bonds present and the quantities of each type of bond which is present. And we're going to add together the bond energies for every single type of bond that's present. That's the summation part. And we're going to say that to make the reaction go, I need to break all of them. So I take all of my reactants basically, and I kind of like decompose everything that's present into just atoms. That's kind of my model here, okay? All the molecules, breaking all the bonds, decompose everything to atoms. So I'm going to break a bunch of bonds. Now, from what you know about chemistry, do you think that that's going to be free, or do we think that it's going to cost us some energy? We're going to break bonds. It's probably going to cost us some energy, specifically the bond energies involved. So this is an energy cost, which means that this step always going to be endothermic, right? It's going to cost us energy. How much? We just need to figure out how many bonds are present. We'll show an example in a second. Now, the second term in this equation that we're going to add to this first one is also a sum term. And that sum term is the bond energies of the products which are formed as a result of the reaction. So remember we said that we're going to decompose all of our molecules into atoms, and now we're going to make new products. Now when that happens, we get new bonds formed, right? Additional bonds are formed that weren't present before. So why don't we just take the bond energies of all the new bonds and add them up, and we'll say that we get that energy back because the system stabilizes. So this second step is going to be treated as an exothermic step, which means it's going to have a negative sign. Okay, so we're really going to end up subtracting that because it's going to have a negative sign, right? Always, because you get energy back when bonds form. Okay, so this is our approach. It's pretty simple. We're taking molecules, we're breaking them all apart, breaking all the existing bonds to a collection of atoms, and then we reconfigure the atoms into the products, considering the new bonds, and we just subtract the bond energies. Okay. Makes perfect sense. And since enthalpy is a state function, doesn't matter how you get from point A to point B, this works. Now, I said earlier that this equal sign is really just an estimate, like an approximately equal to. And the reason why that is, okay, is because this table of bond energies, which was reproduced in these quick notes, it's also there in your book. And on an exam or something, we give you these bond energies. You don't have to memorize them, right? But this table of bond energies, there are certain bonds listed on this table that the value given is really just kind of like an approximate value for that type of bond. So say, for instance, a carbon-carbon bond. There are literally like thousands of different possibilities for carbon-carbon bonds, okay? There's a carbon-carbon bond in this hydrocarbon. These are all H's, okay? That's one carbon-carbon bond. I could take this H and replace it with OH. Now, this carbon-carbon bond may seem like it hasn't changed, but its energy may have changed ever so slightly by putting a different group here, okay? So the thing is that these numbers in the table are really just approximate values of what that bond is like, okay? And that's why this equal sign is really just an approximation. But nonetheless, it's kind of a cool idea if you think about it. We're just listing bonds, breaking some, making some new bonds. We can estimate an enthalpy of any reaction we want to. So if we were going to do an example problem just really quick and kind of talk through it, let's look at this example problem here from our quick notes. We want to estimate the reaction enthalpy, or delta H0 reaction. Remember, the 0 is for standard conditions. And that table was under standard conditions. That's what allows us to write the 0, okay? But the reaction we want to know about is H2 gas plus F2 gas to make 2 copies of HF gas. So it's all a gas phase reaction. So if we're going to think about how to do this, we kind of need to define, well, what types of bonds do we have present in each case? All right? And this is actually why it's in this chapter, I think, is because previously we talked at least briefly about Lewis structures, Lewis dot structures. And you have to actually write that Lewis dot structure to be able to pull this off, because you have to know what kind of bonds we're dealing with, right? And that's, I guess, why it's here and not in the enthalpy chapter. But if I'm going to write the Lewis structure for hydrogen, I would write this, H line H. And remember, that line corresponds to a pair of electrons, or 2 dots, which are shared. It's an HH single bond, right? Now, in the other case, I've got fluorine. We haven't talked much about writing these Lewis dot structures for a lot of different molecules. We're actually going to start that in chapter 10. That's really what chapter 10 is all about. But one of the things you need to do to write the Lewis dot structure is count valence electrons. Now, for fluorine, it's a halogen. It's in group 7A. So I see quickly that each fluorine has 7 electrons. So what we tend to do is we draw these dots after connecting the fluorine atoms, because we need to know that they have to be bonded together. So we'll have one line connecting them, and then a series of dots around the fluorine. Now each fluorine atom has 7, and we've got 2. So we've really got 14 electrons that we need to include in our structure. So let's see if we have that. So 1, 2 lone pairs, 3, 4, 5, 6 lone pair electrons, I should say. 7, 8, 9, 10, 11, 12. So 12 dots, which represent those lone pair electrons. And then I've also got this line right here. And I guess if I was a bit of a Lewis dot structure purist, I may even write that line as a shared pair of electrons, right? Remember, one line corresponds to 2 electrons or a pair. So I've got 2 electrons involved in a bonding pair and 12 lone pair electrons. That makes 14. That's what I had to use. And it looks to me like fluorine is connected with a single bond, one bonding pair, 2 electrons which are shared between the fluorines. And each fluorine also gets 6 lone pair electrons, or each fluorine gets 3 lone pairs. If that makes sense. I always got to be careful with my narration and vocabulary and be very specific about what I'm saying, right? Pairs of electrons versus lone pair electrons, right? So it's a little bit confusing terminology, I guess. But this is what I've got to deal with. Now HF, once I make HF, that's going to have a dot structure that looks like this. It's got one bond between the H and the F, single bond. Okay, so now we know the types of bonds that we're dealing with. We've got to break these bonds to make our HF. And then once we make our HF, we're going to get 2 moles of this stuff. 2 moles of HF single bonds, right? So now we define what we're doing. All right, so let's see what we need to do. So we need to break 1 mole of HH bonds and 1 mole of our FF bonds to pull this off. Now, if we go to that table of bond association energies, we find that the bond energy of H2 is a 432 kilojoule per mole. And that's to break the HH bond. Okay, that's what it cost us. That's the bond energy. And likewise, if we go to look how much energy it cost us to break the FF bond, it's 159 kilojoules per mole. Again, that's our bond energy. Now, in the balanced chemical reaction, we've got a 1 and a 1 as our stoichiometric coefficients for both reactants. So we're breaking 1 moles of the bonds in each of the compounds. So this is what it's going to cost us. 159 kilojoules per mole, 432 kilojoules per mole. So our total cost to break these molecules down into atoms in the gas phase is going to be 591 kilojoules per mole. We just add them together. That's our cost of breaking all of the bonds which are present in our reactants. Make sense? Okay, because it doesn't come free, right? All right, let me erase this over here. Now, what in the world do we get back? What's positive about this, right? Well, if we're making an inventory of what we get back, it looks like we make 2 moles, 2HF, right? 2 moles of hydrogen fluorine bonds. That's what we make once we recombine the atoms into products. You get 2 moles of HF bonds. So we can look up on that table what the bond energy is for the HF bonds. And when we do go and find that, we find out on the table the number that's listed is 565 kilojoules per mole of HF bonds. Now we're going to have to multiply that by 2 because we're making 2 moles of those bonds, right? So when we do that, we get 1130. Now the number that's in the table is a positive number. It's 565 kilojoules per mole. I multiply that by 2. We can see we get 1130, okay? But what I want you to remember is this is the energy that we get back, that we recover when the new bonds form. So again, remember the sign in all this thermochemistry bit tells us like the directionality of the heat flow or the energy flows, okay? Here, this was our cost to break the bond. So we have to put that energy into the system if we're going to get those bonds to break, this 591 kilojoules per mole. But when the new bonds form, we get this stuff, we get this energy back. We get 1130 back, okay? So we have to remember that the sign on this one should be negative. Because when those new bonds form, that energy is released, the system stabilizes, and the energy is released to the surroundings, okay? So with that said, we're then able to return back to this equation of summation that we learned about up here at the top, right? So what was our cost to break bonds? Well, it was a positive 591 kilojoules per mole, wasn't it? So I can compute my delta H reaction by taking that positive 591, and now I'm going to subtract or add a negative, okay? 1130, because that's the energy I get back when the new bonds form, okay? I find the difference, and it ends up being negative 539 kilojoules per mole, and that's what I'm going to expect my delta H reaction for this reaction to be. Okay, so it's as simple as that. All we did is we considered the types of bonds present in the reactants, figured out how much energy was required to break those bonds, and then we figured out what types of new bonds we got in the products and figured out how much energy we got back and just did the bookkeeping. That's it, okay? So it's really kind of an interesting idea if you, I think, if you think about it, because all we're doing is we're looking at which bonds are present. We understand that chemical potential energy can be stored in those bonds. We use that to our advantage. And the fact that the enthalpy of reaction is a state function, it doesn't matter how you get from a certain set of bonds to a certain set of new bonds. If you make that transition from one set of bonds to the next set of bonds, the enthalpy is conserved, okay? So it's kind of a really cool idea. So that's also there at the end of chapter 9 as well. Does that make sense? Okay, awesome. Now with that said, I think what we're going to do is we're going to go on to the next chapter, which is chapter number 10. So let me pull up the notes for chapter 10. That is right here. Awesome. And chapter 10, I like this chapter. I kind of like it a lot more than chapter 9 and chapter 8, just because there's like two major concepts, I guess, here in chapter 10, really three. And they're all, I think, kind of interesting and both interesting and chemically relevant, okay? So chapter 10 is actually a big chapter. It's going to take us probably the rest of the week and the next week to get through. And it's also pretty important as well for your understanding of chemistry. So we'll want to focus on chapter 10. It's a good chapter. So what we're going to start with today is learning more about these Lewis structures, okay? And if you haven't gotten a lot of practice with this yet, that's okay, because we're going to practice it even more in chapter 10 here for quite a bit. Because that's going to be one of our major learning objectives here for chapter 10, is to become real familiar with the process of writing these Lewis dot structures, or Lewis structures as they're called. And what that does for us is it's going to allow us to explain how bonding exists, not only in ionic compounds, but in covalent compounds and molecular compounds or molecules. So we're going to actually dive into that here the rest of class today, talking about writing Lewis structures for molecules. How do we write a Lewis structure for a molecule? And what information does a Lewis structure give us? And what information does a Lewis structure not give us? It turns out that what the Lewis structure is going to do for us is in our molecule, it's basically going to describe bonding, like how the molecule is held together through a series of single, double, or triple bonds, bond order 1, 2, and 3. That's what the Lewis structure does for us. It describes chemical bonding, specifically oftentimes covalent bonding as it relates here to chapter 10. Now, what a Lewis structure alone does not do is it doesn't really tell us about the shape of the molecule or whether it's polar just by itself. Okay, now the Lewis structure might help us understand whether the molecule is polar or help us understand what the shape is. But that Lewis structure by itself, it doesn't tell us about the polarity of the molecule or the shape of the molecule. We're going to need a few extra theories kind of thrown in. Okay, and that's also in chapter 10. That's why it's kind of a big and important chapter. After we get good at these Lewis structures and we practice that a little bit, we're going to learn about something called this VS-EPR theory, which I think is kind of a really cool idea. It's called the valence shell electron pair repulsion theory, which sounds like a mouthful, right? But it's actually a pretty simple idea. As it turns out, what we're going to do is we're going to write a Lewis structure for our compound of interest, our molecule of interest. And from that, we are going to decide that electrons, all being negatively charged, really want to repel one another, hence the word repulsion. Okay, so there are going to be certain electron groups around what we're going to call central atoms, or atoms in the center, in our Lewis structure. And because the electrons want to repel from one another, they basically want to get as far away from each other as they possibly can in space, right? It's like you and your little brother or sister, if you have one, right? You want to be on opposite ends of the house or something, right? Particularly in the age of COVID, right? They might infect you. But anyway, these electrons want to get as far apart from one another as they possibly can. And that's what happens in our molecules. And because of that, the electron pairs repelling one another basically determines the shape or the geometry of our molecule around that central atom. And that's the whole idea behind this VS-EPR theory. That's the whole idea behind how molecules take on the shapes that they do. Is that the electrons get as far apart from one another as they possibly can. And if you can remember that, you're kind of on your way to understanding this VSEPR business and predicting the shapes of molecules, which we're also going to do here in chapter 10. Now, once we're able to predict molecular shapes and shapes around central atoms using this VSEPR theory, we can then decide if molecules are polar, with molecules being the key word here, okay? In the previous lecture, last Thursday, online, everybody learned about electronegativity. On the electronegativity scale, we said that fluorine up at the top right on the periodic table was the most electronegative, right? And we said that metals on the far left, not very electronegative, right? Like most electronegative elements are the top right. The bottom left is the least electronegative. That was our trend. Now, we also learned that electronegativity meant whether or not the atom in the bond really grabbed the electrons and hogged it for itself or not. Okay, we said there could be unequal sharing and highly electronegative elements sort of steal the electrons for itself, right? Remember that discussion from last time? Okay, so that determines whether or not a bond is polar, the difference in electronegativities between the atoms involved in one bond. Okay, in last class, we restricted it to one bond, right? We were talking about computing delta En or the difference in electronegativity between the atoms. And that was just for one bond. Is this bond polar or not? But when we start talking about molecules, many molecules have more than one bond. So what we're going to have to do is consider the polarity not of just one bond, but the polarity of every bond within the molecule. And then we're going to have to do something fun. In 3D space, we are going to have to kind of visualize, using our VSEPR model, whether or not the molecule as a whole is polar or non-polar. And the way that we usually do this is we basically assign these little, remember we talked about these bond dipole vectors or arrows? We assign those vectors along the bond, which is polar in the molecule. And then what we do is in 3D space, we basically add these up. and sum them. Now you can do that mathematically, like in physics class, if you really want to. There's ways to do that, right? Because they have both the magnitude and the direction. But for our purposes in our class, we kind of just do this mentally to see whether or not the vectors cancel out or they don't cancel out. And in many cases, it'll be once you get the Vesper theory down and you understand how these vectors work, it'll start to become more obvious whether they cancel or not. Okay, there's some rules for that you could write on a piece of paper if you want to, but usually we just do it kind of mentally, and we'll explain how to do that as we move on. But these are the three big objectives here for chapter 10, all of which are really super important as you move forward in chemistry. Because if you're going to take Gen Chem 2, if you're going to take organic chemistry, the shapes of molecules, particularly in organic chemistry, start to become really, really important, okay? And molecular polarity actually determines whether or not molecules are very, certain substances are very viscous, or if they have a high or low boiling point, if they melt easily, because it's something that we're going to learn called intermolecular forces. And to learn about intermolecular forces, which is actually kind of another really interesting thing, it can describe lots of bulk properties of materials. But to learn about intermolecular forces, you have to be able to figure out whether or not molecules are polar. If you can't do that, you're going to kind of be stuck, okay? All right, so these are our major objectives. So today, my hope is to tackle the first one, which is about Lewis dot structures. We'll talk about writing these Lewis dot structures, gain some practice with this. You'll also see the practice in the Connect homework, okay? It's definitely a skill you want to know for next week's exam. And then we're going to sort of fill in some vocabulary with regards to Lewis dot structures, which are going to include resonance forms or resonance hybrids. We'll also talk about something called formal charges along the way. We'll define what that means as we go, okay? But all this kind of goes together with writing these Lewis structures. Now, the Lewis structure, again, ultimately what that does for us is it describes the bonding pattern or the pattern of bonds in our molecule. It describes which bonds are present between which atoms that hold our molecule together. That's what a Lewis structure is all about. Now, let's talk about how we're going to start writing these for molecules. There's like the stepwise approach that I saw on the slides. And I don't know, maybe this slide's a little bit wordy, but I guess it does provide us some guidance for the process that we're going to go through over and over again. So I kind of wanted to start here, all right? So what we want to do is we want to write a Lewis structure that describes bonding in our molecule. Now, we don't get there right away. We follow a sequence of events. The first of which is by identifying the molecular formula. This is like CXHXNY, right? How many atoms of each type do you have in your molecule? This is our molecular formula. We're all familiar with chemical formulas, right? So you identify that first, maybe write it down on your piece of paper. Usually that's given to you. Now, after you identify that molecular formula, the next thing that you do, and this is if your molecule has one central atom, sometimes we'll have more than one, okay? But as a general rule, atoms with the lowest electronegativity like to be central atoms. And you'll find some rules along the way for central atoms, and you'll start to become more familiar with what types of atoms can be central atoms and which time can't ever be. Because sometimes there are definite trends. Certain elements like to kind of be in the center, and other elements don't ever. But what a central atom is it's basically like the one that's in the middle, that's bonded to multiple different atoms. It's called a central atom. One that's bonded to multiple different things. And identifying a central atom is actually pretty important, because once we start to talk about geometry with that Vesper model, the central atom, the geometry is going to be, of the molecule is going to be described by the geometry around these central atoms. Okay, so we have to kind of identify them. Now, just as a general rule, I can kind of give you some hints. It turns out hydrogen will never be a central atom. Never, ever, ever. Because hydrogen, as it turns out, when we're going to write these structures, we'll seek what I'm going to call a duet of electrons, which means two. Hydrogen seeks two electrons because if it gets two and shares two, its valence shell will be full. Okay, because hydrogen, what you're looking to fill for hydrogen is that, you can think about it this way, that 1s atomic orbital is what's looking to fill, which can only hold two electrons. So hydrogen always seeks a duet or two electrons, which means hydrogen will only form one and only one bond. Always. Hydrogen forms one bond, that's it, nothing else. Because once it does, it's achieved its pair of electrons, its duet of electrons, and it's good, it's set, okay? So because hydrogen only forms one bond, it will never, ever, ever be a central atom, all right? First thing to know. Carbon, on the other hand, is almost always central. It's like the opposite of hydrogen. Carbon almost always is a central atom. Carbon typically likes to form four bonds. These are just kind of like general rules to get us by. I'll show you, go through this procedure here later, but these are just general advices. Yeah? Hydrogen never in the center, carbon almost always in the center. Now, beyond these two elements, which are pretty popular in chemistry, okay? The atom with lowest electronegativity tends to be in the center. So if you've got some kind of different compound that you're not familiar with, and you need to figure out which atom's in the center, and particularly if there's only two choices, choose the one of lower electronegativity. That's the one that's going to be the central atom, okay? We'll see that as we go along. So you put that one in the center. And the next thing that you do is you place the atoms, the remaining atoms, around that central atom. Now in the Lewis dot structure, you might put the low electronegative element in the center. And then people always kind of like worry about like where to put the other atoms, you know, can I just draw them any which way? And the answer is generally yes, because Lewis dot structures in their own right do not really infer molecular geometry. You need the VSEPR theory to help us do the geometry. So you can kind of distribute them however you like around the central atom. All right. Now the next thing that we're going to do is we are going to add up valence electrons. We're going to go to our periodic table, identify the elements on the periodic table. And usually we're going to be using main group elements for this, okay? But we're going to simply sum or add up all of the valence electrons for all the elements that we've got. The reason being is these are the valence electrons that we're able to use to form chemical bonds. These are the electrons we're able to use. Remember, valence electrons, those in the outermost principal quantum level, are the ones which are used in chemical bonding. So those are the ones that we're going to add up. We're going to sum them and we're going to use those valence electrons to make bonds. So step 3 is drawing in those single bonds to connect the dots, to connect the atoms. We're going to connect the atoms in the periphery or around with the atom in the center, the central atom, by drawing single bonds at first. Now remember, each line, each single bond counts as 2 electrons, a pair of electrons. So by drawing in a line, we're going to use up, if you will, some of these valence electrons to connect the whole molecule together. Each line counts as 2 electrons. All right? Now, after you do that, chances are you will not use all of your electrons. You're going to have some remaining. And then what you do with the remaining valence electrons is you distribute them to all of the atoms in your structure with the guiding principle that hydrogen gets 2 electrons total, but other elements in the main group seek 8 total. This is going to be called our octet rule. Okay, so hydrogen gets 2, but other main group elements seek 8. Our octet rule. And that's so they basically, we can think of it as so they're filling up their S and their P type atomic orbitals to get that full valence shell like the noble gases. Okay, that's how we could kind of rationalize that from an atomic orbital perspective. Okay. And in doing this, by placing these individual dots, distributing these remaining valence electrons, oftentimes that's going to allow you to come up with an acceptable Lewis dot structure, but sometimes you'll find that you use too many electrons if you give each of them 8. And in that case, you have to share more, which usually involves making double bonds or maybe even triple bonds, okay? So there'll be a series of quality control checks that we make at the end to make sure that we've used the right number of electrons, right? So I think that maybe it's just best to kind of dive in and do an example of this, all right? So why don't we try to write together here a Lewis dot structure for this molecule, NF3, nitrogen trifluoride, okay? So if we're given that molecule, we want to kind of follow this protocol. The first step is to try to figure out which atom goes in the center. Now we know from last class, and hopefully even today, right, because we memorized this, that fluorine is the most electronegative element. So is fluorine ever going to be a central atom? Nope, it won't. Nope, fluorine is not going to be a central atom either. It's always on the periphery. Now nitrogen is still pretty electronegative, but of these two, it's our lower electronegativity. So because of that, by that first rule or step 1 that we talked about on the previous slide for Lewis dot structures, we decide that nitrogen is placed in the center. Reason being is you always put the lowest electronegative element in the center. So nitrogen goes in the center. We start off with something like this up here at the top. Nitrogen in the center, and then we've got F3, so we put the fluorines in a triangle. Oftentimes you can put the remaining atoms, just spread them out as far as you can around the central atom. That's kind of common. But remember, these Lewis structures do not infer a particular geometry just in their own right. So that's where we start. Now we start figuring out the bonding pattern in this molecule. To figure out the bonding pattern, the next step is counting all of the valence electrons, and only the valence electrons, which are available to us, okay? So let's look at nitrogen first. Now nitrogen is atomic number 7, Z equals 7. So I'm going to write the full electron configuration, and then we're going to figure out which are the valence. So I got 7 electrons. I fill up my 1s2, that's 2 of them. And then I go to my 2s2, because that's my next allowed atomic orbital. That gets me to 4, and it looks like, gosh, I got 3 more, which are going to go in my 2p3, aren't they? That's my full SPDF electron configuration for nitrogen. And the question then becomes, is which of these are valence electrons? And remember, the valence electrons are only the ones in our outer principal quantum number. Here, that's n equal 2. So my valence electrons in nitrogen include the 2s2 and also the 2p3. So each nitrogen atom has 5 and only 5 valence electrons. Now I need to figure out fluorine. So I do the same type of thing. So fluorine is a couple elements over from nitrogen. It's atomic number 9. It's got 9 electrons. So I do the same thing. 1s2, 2s2, 2p5. Which are my valence? Well, the n equals 2 levels, my valence for fluorine. So each fluorine has how many valence electrons? 7, right? So that's my first step, counting valence electrons. So you have to identify the valence electrons to be able to do that. So you can write the full electron configurations like I did, figure out which ones are in the highest end. Sometimes people do that, that's just fine. Another approach that you can use is to look at the group number in the main group elements from the periodic table, and that also tells you how many valence electrons are present. So for instance, fluorine is in group 7A, so we know it's got 7 valence electrons. Nitrogen is in group 5A, so it's got 5 valence electrons. So this is our thought process, okay? All right, so this inventory is for each atom. Now we're going to put these atoms together to make a molecule. So how many total valence electrons do we have? Well, we've only got 1 copy of nitrogen, which gives us 5. So we have 5 valence electrons to play with from the nitrogen. And each of our fluorines give us 7 for a total of 21. because each fluorine brings 7 to the table. We've got 3 of them. So the total number of valence electrons to establish bonding in this molecule is 26. We've got 26 electrons we're able to use to make the required bonds. All right, so now that we've figured out how many valence electrons we have to play with, we go about connecting the dots, connecting the atoms together. We know that this molecule is going to exist, it's going to stay together and be stable, so we need to have bonds to hold it together. So that's what we do. We draw in lines to connect the dots to the central atom. Remember, each line represents 2 dots, or a bonding pair of electrons, right? Each line is a bonding pair. It's one of our terminologies, right? Our vocab words. So I have 3 lines because I need to make 3 bonds to hold the nitrogens and the fluorines together. That's my next step. I'm drawing in single lines, single bonds from the central atom to each of the atoms on the periphery, whatever they are. Here it was fluorine, okay? All right, now step 4 then is to fill in the blanks. And what do I mean by fill in the blanks here, okay? Well, notice right now that this fluorine, it has what I might say is an incomplete octet as it's drawn right now, okay? And what I mean by that is each one of those fluorines is involved in a bond, that single line, but that bond only involves sharing 2 electrons, right? Each bond is sharing 2 electrons. So right now, each fluorine really only has 2 electrons associated with it. And it wants to have 8, right? It wants to have an octet, as we like to say, because that seeks that noble gas configuration. Likewise, the central nitrogen right now, it's doing a little bit better off because it's got 6 electrons associated with it, right? 2, 4, 6. Each line corresponds to 2, but it's still short of its octet. So what we need to do is we need to fill in the blanks, so to speak. And we do that by distributing remaining electrons as lone pairs on all of the atoms, okay? Such that each atom ends up with its octet or its duet for hydrogen, because hydrogen just needs 2, right? Okay, don't forget that. So that's what I'm going to do. So I'm going to come back, I'm going to draw on my lone pair electrons. I'll start on my peripheral atoms. Now I'm looking at each fluorine and I see that it's got that 1 bond, which is 2 electrons. So I do the quick math in my head and say, well, for my fluorine to get to 8, I need to add in 6 more dots or 6 more electrons, which means 3 lone pair electron sets, okay? And I do that for each and every fluorine because each and every fluorine needs to achieve the full octet. But I'm not really done because I look at that central nitrogen and I say, okay, it's got 3 bonds, which means it's participating in sharing of 6. But that central nitrogen really needs to have 2 more. Oops, okay, I need to do this. Central nitrogen really needs to have 2 more to get to 8. So I draw in those dots. That's my first attempt at a Lewis dot structure, okay? So my guiding principle was to connect the atoms together with bonds and then come back and add these lone pairs. All right, everybody see that? Now there's nothing wrong with what I have here, but I haven't really considered if this is possible or if this could be correct yet. Now I just kind of like said, oh, this looks like what it should be, right? But all my atoms only have 8. Okay, this is the way to do it, right? But now I have to assess the validity of my Lewis dot structure. And one of the first ways that I do that is I have to count the electrons that I've used and compare that with how many I have available. Now earlier I said I have 26 available. boy, my structure better have used 26 if it's going to be correct. If I've used 24, it can't be correct. If I've used 32, it can't be correct. I got to use 26. So after you propose your Lewis structure, like to explain the bonding, you always need to come back and check and assess that structure's validity. And the first quality control check is counting electrons. You have to use the number of electrons that you were given. Okay, it's a must. We were given 26, we need to use 26. So that means that we just have to go counting. Okay, let's do that. So I'm looking at this structure, and I'm thinking of the fluorines first, okay? I've got 3 fluorines, and each of them have 6 lone pair electrons. This is LP, lone pair. They've got 6 each. So that gets me to 18. The ones that I counted, just if you're not following along, it's these right here. Each fluorine's got 6. Those are our so-called lone pair electrons, right? Those are the ones I counted to get to 18. Now that central nitrogen has 2 such electrons. Right there. So now I've counted all my lone pair electrons. But you see, I'm only at what? 20 right now? Okay, so where are the other electrons? Well, oops. Didn't we build 1, 2, 3 bonds? Each bond has 2 electrons. So we built 3 bonds, each one using 2, which get to 6. So if I add all those electrons up, I've used 26, and I had 26 available, right? So because of that, this structure then passes our first quality control check. We've used the correct number of electrons. That's a must. You always have to use the correct number of electrons. You can't ever not use the right number of electrons, okay? So we would look at this structure, and we'd say, yeah, that's a possible Lewis structure for this molecule. Okay, that explains the bonding. It uses the correct number of electrons, all right? That makes sense? Okay, so with that said, let's practice this just a little bit more, okay? And maybe write a few more Lewis dot structures. Let's look at this one right here. CCl2F2. Now that's got 3 elements, doesn't it? Carbon, chlorine, and fluorine. Earlier in class today, I kind of gave you a pretty hard and fast rule about carbon, right? Remember carbon? Carbon always liked to be in the center or central atom. And even if you were looking at electronegativities from these 3, you'd say, oh, carbon's got the lowest electronegativity. Fluorine's the highest. Chlorine is kind of up there. Carbon's the lowest, so we're going to put that in the center, and indeed we will. And then we've got 2 copies of chlorine and 2 more atoms of fluorine as well, right? All right, so why don't we just put carbon in the center, chlorine, chlorine, fluorine, fluorine. I'm drawing in my lines because we're always going to do that already, but I haven't counted valence electrons yet, but I'm about to do that now, okay? So we go to the next step. Central atom was assigned. Now we need to figure out how many valence electrons. So we go to our good friend, the periodic table, right? We open up our book. We find the elements. Now, it looks like carbon is our first element. It's in group 4A of the periodic table. So carbon is going to have what? 4 valence electrons? Not 4 total, 4 valence. Remember, I'm just counting my valence electrons. That's important. Chlorine and fluorine are my other elements. Now, each atom of these elements have 7 valence electrons because they're in group 7A. They're halogens. All the halogens have 7 valence electrons. So now that I've found these positions on the periodic table, I can add up the total electrons that I've got to work with. My molecular formula tells me that I've got 1 atom of carbon. I've got 2 atoms of chlorine, and I've got 2 atoms of fluorine. So if I'm adding together all my valence electrons, it looks like I got 14 plus 14, 28 plus 4, that's 32, right? I've got 32 valence electrons to play around with. So I put my carbon in the center. I put the other atoms around the carbon. Again, it does not matter if you put the chlorines across from one another or the way I have it drawn, because again, the Lewis structure itself does not infer any molecular geometry. It's just the pattern of bonding. Now I got to think about, well, what do I need to do to fill in this Lewis structure? Now, earlier, I already kind of automatically drew in these single bonds, which is the first thing that you always do, okay? To connect the dots. You got to hold the molecule together. Now, that's 4 bonds, which means 4 bonding pairs. Each pair's 2 electrons. So right now, I've used 8, just the way that structure stands. But of course, I'm not done yet, am I? And I look at the structure, what's wrong? Well, I got to fill in my octets, right? And as I'm looking at it, the chlorines and the fluorines, they seem to be involved in 1 bond right now, but that's it, right? They're not in bond, they're not, they don't have any extra electrons other than that bonding pair associated with them. So we have to complete their octets. So we do that by assigning each atom an octet. So I put 6 red dots around the fluorine. Doesn't really matter what atom you start with. I started with that because it's the most electronegative, but it's not really all that important, the order that you assign the dots. Just that every atom gets its octet. So I put 6 dots for each of the atoms, the chlorines and the fluorines. Now I did not put any dots for that central carbon, all right? How come I did not put any additional dots? How many electrons are associated with that center carbon right now? Does it have 8? I think it does, right? That central carbon's got 4 bonds, 4 bonding pairs associated with it, which means, well, 4 bonds, 2 electrons per bond, that's 8 electrons. So that's already got its full octet. And remember I said earlier that the carbon likes to form 4 bonds? We can see that here, okay? And the next question is have I used the correct number of electrons? I think this is going to be right, but we need to double check, okay? Now we said the bonds have used 8. Now what about our lone pairs? Those are the red ones, right? Well, it seems like there are 6 red dots on each of these peripheral atoms, of which there are 4. So it seems to me that we've got 24 lone pair electrons. We used 8 in bonding pairs, 24 in lone pairs. We add them all together, that gets us to 32, which is what we had to use. So we pass our quality control check as a result. All right, we're good to go. One more. Let's try PCl2. This one's different for, I think, a couple reasons. But we're going to follow the same exact process to start. PCl2. Note that it's also -1. Don't lose sight of that. That's one of the big differences here, okay? All right, so what do we do? What's the first thing? Figure out which is our central atom. And I'm looking at my periodic table. Phosphorus is 2 boxes to the left of chlorine, which means the phosphorus is less electronegative. Phosphorus is generally always the central atom as well. If you see phosphorus, it's going to be in the middle, okay? So I put that one in the center, and I distribute my chlorine atoms around it, of which there are 2. Okay, so I'll start with something like this. Now I go about doing the same thing. How many valence electrons, okay? So I look at my periodic table, phosphorus is right below nitrogen, so it's a member of group 5A, so it seems like phosphorus has 5 electrons in the valence shell. And each chlorine, it's a halogen, so it's got 7. So if I'm considering the atoms in my formula, I've got 7 plus 7 plus 5. Let's see, that's 14 plus 5. I think that gets me to 19, right? Now, do I want to draw my structure with 19 electrons or a different number? And I'll highlight this again. That negative sign right there in the formula, that's kind of important here. What does that tell us? Doesn't it tell us that that cluster of atoms or that molecule that's bonded together here, it's an ion, right? It's got a charge. Doesn't it tell us that ion has one more electron than what it kind of should from the periodic table, right? So the thing is if you're dealing with an ion, like we're dealing with that here, you have to account for the charge of the ion. And since this is a -1 ion, we've got to add an extra electron. So we actually have 20. Because the whole thing, the cluster of atoms bonded together, it's got one more electron than it should, just based on the atom's position on the periodic table. So we add that back in. So don't forget that. If you're ever dealing with an ion, if it's a negatively charged ion, an anion, you add electrons to use. But if it was a positively charged cation, we would have to subtract the electrons, okay? All right, so don't lose sight of that. If it's an ion, you gotta figure that in. All right. But now we know that we've got 20 electrons to use. So we start by drawing in our bonds. Single bonds first between the phosphorus and the chlorine. And then we would go about completing our octets. So I would do dot, 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 dot. Also 6 dots over here. 1, 2, 3, 4. This will be my first structure I propose. Now we have to check and see whether or not the number of electrons we've got is what's reflected in our structure. So let's see, how many lone pair electrons do we have, okay? So if I was to highlight them, let's say 2, 4, 6, 8, 10, 12, 14, 16. My count was correct. I think we had 16 lone pairs of electrons. Is that right? Okay. And then how many bonding pairs? Bonding pair electrons, I guess we should say. How many? Okay, so is that how many that we had to use? Would that be okay then to do this? All right, so it kind of passes this quality control check. All right, fair enough. All right, so what about then some more complicated examples, we'll say, trickier ones. There's a series of different tricks that we'll get into eventually here, okay? And this is one of them. Some molecules will have more than one central atom, more than one atom in the center. Now, the examples we've got, these are kind of simple examples so far. They just had one central atom, and we could explain the bonding just with one atom in the center. But many molecules, particularly these organic molecules, will have multiple central atoms. So what would an example of bonding in those molecules look like, okay? So to help us understand this, let's think about an alcohol called methanol. It's got this molecular formula right here. We want to draw the Lewis structure for methanol. Now, methanol, it's got one less carbon than ethanol. Ethanol is like the drinking alcohol. Methanol has only got one carbon, hence the prefix meth, okay? That's a common prefix in organic chemistry for a one carbon compound. So that's kind of what we're using here to denote it's got one carbon. But this alcohol is actually really dangerous. If people drink it, it's poisonous. It causes them to go blind. You lose your eyesight. So you'd never want to drink methanol. But it's got the molecular formula CH40. It's used in industry, so on and so forth. So how can we draw the Lewis dot structure for this molecule? Now, earlier today, I said carbon is always a central atom, and that's gonna be true here. It's not very electronegative, and it's almost always a central atom. I can't really think of examples which it's not. But in methanol, it turns out that we're gonna have a second central atom as well. There's gonna be a second element, which is in the middle and bonded to multiple things. Now, based on our rule earlier, can hydrogen ever be a central atom? It can't. So we know that oxygen must be a central atom as well by that logic, okay? And that's going to be the case here. Now, these two are going to be bonded together through one bonded linkage, and we'll explain how this molecule works here in a second. But at this point, we've got 4 hydrogens that we're going to have to distribute somewhere. We're going to have to think about that a little bit down the road, but I guess we should maybe start just continue by counting up our valence electrons. So we've got 4 copies of hydrogen, CH40, right? Each hydrogen's bringing along 1 valence electron for 4 to use in bonding. We've got 1 carbon. Carbon's a member of group 4A, so it's got 4 valence electrons. It brings along 4. We've also got a copy of oxygen. Oxygen is a member of group 6A, so it's got 6 valence electrons. You add them all together, it looks like we've got 14 electrons to build a structure out of, 14 valence electrons to build our structure out of, okay? We know that we've got to link our carbon and oxygen together. So from here, we got to figure out where these hydrogens go. Now I've got 4 hydrogens that need to get added into this structure. Where do I put them? Now, to help with this, we have to consider there's a number of possibilities. I don't know what the best way to explain it is, but let's see, 4 hydrogens. I guess I could do something like this, right? Okay, hydrogen, 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 hydrogen. All right, so that's what I could write if I wanted to, right? That's not necessarily the correct answer or the best way to arrange the bonding pattern in this molecule, but I could write that. Now, if I did write that, how would I know that maybe this was not such a good idea? Any ideas on which of these principles that maybe I violated by writing this structure?
Octet rule.
What was it?
Octet rule.
What about this central carbon right here? How many electrons are associated with it right now? How many bonds does it have?
Has 8.
Does it have 5 bonds? Which would mean that 10 electrons are associated with it. Now, sometimes certain elements are going to be allowed to have what's called expanded octets, but carbon is not one of them. Carbon can only ever have 8, okay? So I've exceeded carbon's octet by arranging the molecule this way. So that can't be right, okay? So what that means then is that carbon really can only have 4 and only 4 bonds. And one of them's got to be the oxygen, because that holds our molecule together. So I could put 3 additional bonds, carbon to hydrogen, in my Lewis dot structure. And if I do that, now my central carbon has 4 and only 4 bonds, which is what it wants. Now I note that in my formula it was CH40. I've only used 3 of the H's. I wonder where the other one goes. Well, maybe it can bond to that oxygen. And in fact, this linkage of atoms in organic chemistry where that oxygen bonds back to a carbon is what makes the functional group called an alcohol. Single bond carbon, oxygen, single bond H. That makes a so-called alcohol functional group when it's like that, okay? So it turns out that this is the arrangement then that works. But I'm not done with my Lewis structure, because what I need to do is now account for all my electrons. Now I've drawn in my bonds, but I haven't completed all my octets. Can anybody see where the some of the octets are not complete? Maybe right on that oxygen? Now that oxygen's got 2 bonds, but to complete its octet, I need to write in 4 lone pair electrons. Because remember, each bond counts as 2. So that oxygen's got 2 bonds, which accounts for 4 electrons. And now it's got those 4 dots, the lone pair, which account for 4 more, to make a total of 8. So the oxygen now has a complete octet as it's written. Now what about these hydrogens? Each of the hydrogen has 1 line. Is that okay, or do we need to have the hydrogen have 8? Nope, remember, hydrogen only always gets a duet, which means 2. Hydrogen only in these structures, it's going to form 1 bond, and that's really all it's ever going to do. Okay, hydrogen forms 1 bond, that's it. Carbon generally likes to form 4 bonds total. Oxygen usually likes to form 2 bonds. Kind of where it's comfortable. It's comfort zone. Okay, chemically speaking. So let's take a look at see whether or not this structure that we've proposed now with complete octets and duets makes sense with regards to how many electrons we're given. So we're going to count electrons. So how many bonds do we have? Let's see. 1, 2, 3, 4, 5. Just counting bonds, right? I've got 5 bonds, each involving 2 electrons. So I've tied up 10 of my electrons in the 5 bonds that hold this molecule together. Now, in addition to that, I've got some lone pair electrons on that oxygen. And it looks like I've got 2 lone pairs for a total of 4 lone pair of electrons on that oxygen. So total, I've used 14 electrons in my structure, and that's what I had to use. So again, this passes our initial quality control check. And indeed, this is the Lewis structure for this alcohol called methanol. This is what it would look like, okay? And again, implied here in this sample problem is, a lot of these really common trends that we're going to see a lot in these types of problems. You can almost use like pattern recognition to help you along the way. Hydrogen, it's always going to form 1 bond. Oxygen likes to form 2, and typically we'll have 2 lone pair electrons. Oxygen can be a central atom. It may not always be a central atom, but it can be because it can form 2 bonds. You need to at least be able to form 2 bonds to be a central atom. And carbon almost always is a central atom. Carbon likes to form 4 bonds, all right? So these patterns you're going to see over and over and over again. So long as we move through this section, I definitely want to try to point out some of these things that consistently come up. All right. Now, what else can come up to make your life more difficult? Sometimes in our molecules, we might have multiple bonds present. We might have a double bond or a triple bond. How will we know when one of these bonds are present and or required? The answer is, you will know that multiple bonds between atoms are necessary when there are not enough electrons for all the atoms to obtain an octet in your structure. In other words, if you go about writing your Lewis dot structure, you put in all your bonds, you put in all your dots, and you count up all the electrons that you use, and you find that you used too many, something is wrong. In other words, you used more than what you actually had. You had 20 valence electrons and you've used 24 in your structure. That does not pass your quality control check. Now, we haven't seen an example quite like that yet. We're going to work one in a second, okay? But if you use the wrong number of electrons, something is wrong, okay? And if you use too many, what that means is that you've got to share some more. And you share more electrons by making multiple bonds in your Lewis dot structure, okay? So let's take an example of one of these questions here. Let's think about writing a Lewis dot structure for ethylene, which is this molecular formula. It's an important reactant to make polymers, okay? We can also talk about nitrogen here in a second. But let's write Lewis dot structures for these. So if I'm looking at ethylene, I say, okay, carbon and hydrogen. This is easy, man. Carbon's always a central atom, so I'm going to put that one in the middle. Again, pattern recognition. And it looks like here I'm going to have two central atoms because I've got two carbons. I'm going to connect them just to remember that, okay? And then I've got these four hydrogens that I'm going to have to distribute around. I don't know exactly what that's going to look like right now, but we'll figure it out here in a second, all right? Let's count valence electrons. Carbon is a member of group 4A. So I've got two carbon atoms, each bring 4 valence electrons for 8 total. And I've got 4 hydrogen atoms. Remember that first group brings 4 more. I've got 12 electrons to use. I'm able to use 12. All right, so I guess, if I'm thinking about arranging the hydrogens around the central atom as symmetrically as possible, sometimes people say to do that with these Lewis structures. I guess I would give 2 hydrogens to each carbon, and I'd probably do something like this. Okay, so C2H4, but now I need to complete my octet. So let's see, my carbons right now only have 3 bonds, so probably what I would do is I'd say, okay, dot, 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 dot. And if I did that, my central carbons would now have 8 electrons associated with them, right? 3 bonding pairs, 1 lone pair. And my hydrogens would have their duets, so everything would be quote unquote happy. But now I got to do my quality control. Check. How many electrons have I used? I'm able to use 12, but let's see how many I did use. So how many bonds? Let's see. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep. Now each bond is 2 electrons, so my bonds have used 10. And let's see, now I got to count my lone pairs of electrons. It looks like I've got 4 of those. My structure has used 14. That structure requires 14 electrons, doesn't it? Now, how many did I have to use? 12. So I got a problem, right? What I drew cannot be correct because it's used the incorrect number of valence electrons. That's a big deal. Cannot do that. So at this point, I have to go back to my structure and revise it. I have to say what I proposed cannot be correct, and I need to do something different. Now notice that I used too many electrons. I used 14 and I only had 12, right? I can get around this problem or fix this problem if I share additional electrons. And that's what I have to do. I have to make use of what the molecule's got to make use of what it's got. It's only got 12. We need to share more, okay? So what does that look like functionally? Well, if we're going to share more electrons, we take these lone pairs and we erase them. Erase the lone pairs first. And then you draw in an additional bond. You increase the bond order, which basically shares more electrons, okay? Now the beauty of doing that is that that additional line that I just drew in between the carbon atoms, those 2 electrons are now counting, if you will, for both carbons, right? So if you let's see. If you, okay. If you reevaluate how many valence electrons we've got now, that carbon has got 8 because it's got 4 bonds. That carbon's got 8 because it's got 4 bonds, right? So both those carbons are happy. The hydrogens still have their duets. And if we go back over here and reevaluate, how many bonds do we have now? 1, 2, 3, 4, 5, 6 bonds. So we're using 12 of our electrons in those bonds. Do we have any lone pairs? There's no dots by themselves, right? So we have 0 electrons in lone pairs. Our structure has used 12. And look, that's what we had. So now we pass the quality control check, don't we? By sharing additional electrons, we can make it work. So this is the type of example that you might see when you're thinking about writing these Lewis structures and you need to make multiple bonds. If here a double bond was required to make it work, sometimes you might even need a triple bond, okay? Let's work nitrogen, N2, real fast here. Nitrogen's on group 5A of our periodic table, which means it's got 5 valence electrons. So we've got 10 total electrons to use in our N2. Now N2, it's only 2 atoms of nitrogen, so gosh, we're just going to connect them together with a single bond, N2, and now we would go about completing our Lewis dot structure. If I'm going to complete my octets, because remember, nitrogen wants to have 8, I would probably start by doing something like this. But if I did that, let's see how many electrons we used. Well, I used 2 in the bond, and then it looks like each nitrogen has 6 more, so that's 12, right? I think I used 14 here in this structure. But I only had 10, didn't I? That's a big problem. I can't use 14 if I've only got 10. So I got to revise. We know that this structure is not correct. Looks like I got to do quite a bit more sharing. And the way I can tell that is looking at the difference between these two numbers. I see that I've got a 4 electron difference. It turns out if you take the difference between what you've got and what you've used and divide it by 2, that tells you how many more bonds you need. So here I know that I'm going to need 2 more bonds. Right? I'm not even close. I need to share more electrons. So I need 2 more bonds. It looks like the only place I can put it, gosh, right here and here. I need a triple bond. Not a double, but a triple bond between my nitrogen atoms. I fill in my octet here and here so that each nitrogen has 8. Now it's got 6 bonding electrons, 2 lone pair of electrons, right? But each nitrogen's got 8. And now if I do my analysis of how many electrons I've used, it looks like, okay, I've got 3 bonds, so that's 6 electrons involved in the bonds. And then I've got 4 more in the lone pairs. That makes 10. Hey, that works. That's what I've got. So it turns out in N2, nitrogen, the gas that floats around in the room, there's actually a triple bond or a bond order of 3 between the nitrogen atoms. That's essentially like the strongest bond there is in general. And because of that, nitrogen is quite an inert gas, okay? In other words, it doesn't readily react with anything. It's quite inert. I mean, you can force that bond to break if you put a lot of energy into it, but it's not necessarily the easiest thing to do. And it turns out as a general rule as well, gases that tend to build up to very high concentrations in the atmosphere tend to be pretty inert because that's how they got there. They didn't react with anything. They stay around a long time, right? And air is about 78% nitrogen by volume or pressure. So indeed, it is pretty inert because it's got that triple bond. But this is an example of nitrogen, okay? All right, so last minute of class here. Just what are some other things that we can see as we're looking towards Thursday's class? We're not going to have time to do this justice today. But for some molecules, we can draw what's called resonance structures. And invariably, this is always kind of a confusing idea. It makes sense why it's confusing, but it need not be. What a resonance structure is going to be is it's actually going to be like a hybrid of 2 different Lewis structures that are shown here. This is actually the molecule O3, which is ozone. And when we go through this next time, we'll draw its Lewis structure. It'll look like this, okay? But it turns out that you can draw the Lewis dot structure for ozone in 2 different ways. They're shown here. Turns out there's a double bond in this molecule. It's going to be a little bit of a bent molecule, but we'll get to shapes later. But the question is do you put the double bond there or there? There's got to be one double bond to make the number of electrons work out. And again, we'll go through this fully next time. But where do you put the double bond to make it work? Which side? Does it matter? It turns out, interestingly enough, that in the ozone molecule, if you go into the lab and make ozone and study it, and you study the properties of this bond, and you study the properties of this bond, experimentally, you make observations on the bonds, they're exactly the same. You cannot tell them apart. And you say, well, how can that be? I mean, the double bond's got to be there or it's got to be there. But in reality, what we're doing with these Lewis structures are just like drawings or pictures, cartoonish pictures on paper to explain the bonding in molecules. In reality, these electrons are shared both places. We like to say that they're delocalized electrons. In other words, the double bond's not here, nor is it here. It's both places in a 50% sense simultaneously, if that makes sense. And that gives rise to what we're going to call resonance structures or resonance hybrids. So we're out of time. We're going to have to consider that next time. But I will see you all then. And again, we're back meeting in person if you prefer that format. Have a good rest of your Tuesday. We'll see you real soon. Bye-bye.